Hello everyone. Welcome back to the course on time and space complexity analysis. I am Sanket Singh, and in this lecture we are going to continue our discussion on problem solving around calculation of worst case complexity of different algorithms. In this playlist we have already completed that why efficiency of algorithm is important, how do you measure the algorithm with respect to hardware, and how a single CPU core system works. We already talked about rate of growth and asymptotic analysis. And even in the last lecture, I already talked about a few problems and how you can calculate the big O notation based worst case complexity for them. In this lecture also, we are going to solve around 3-4 more questions, which are going to give you better clarity that when you actually see an algorithm, how you should move forward to calculate the complexity for it. In my opinion, understanding how complexity of algorithm is calculated gets more clear when you solve more questions or you see more algorithms and try to calculate complexity for them. It's not a one time process. You need to be iterative in that. And this playlist is going to focus on that. We are going to solve a lot of questions where we will be calculating the time complexity of different algorithms. This lecture is going to be part of a bigger playlist that we are building for time and space complexity analysis to make sure that you guys get a good grip on this particular topic. So without any further delay, let's just start and let's start solving our first question. So now let's start talking about how you can analyze the complexity, time complexity, space complexity for a recursive code. Till now we have done everything with respect to a iterative piece of code. Now we need to talk about recursive code. So overall the theory remains same. The theory remains same, that is we have to do the time complexity analysis using the number of instructions executed, right? We're going to again use how many number of instructions are total executed with respect to the input, right? The time is going to be measured as a unit with respect to the number of instruction executed to the given input. As the input will grow or as the input will change, the number of instructions will change, and hence that will lead to a change in the time complexity analysis. Okay, cool. Now, technically in recursive codes, there are two techniques. One technique that we are going to talk about today, right? One more technique is going to be used for some specific type of recursive relations, right? Those are called as divide and conquer relations. Although the baseline theory still remains same, that you have to figure out the number of instructions executed. But we can formulate a few general situations for both of them, right? So the underlying behavior is going to be same, that we have to see the number of instructions that are going to get executed with respect to the input, right? First of all, let's just take our basic recursive codes. So let me take a code like this in front of you, right? So if you just carefully see, then this is a normal factorial function. This function can calculate factorial for you. See, this is the recursive relation for factorial, right? F of n is equals to n into f of n minus 1, right? Okay. Now we have to calculate what is the time complexity for this factorial function. Now the time complexity we have to calculate based on the fact that how many total instructions were executed in order to calculate n factorial. How many total instructions were executed to calculate executed to calculate n factorial, right? Now just think about it. Here we don't have a loop. Right? Instead, we are using recursion to repeat the process. So how many total instructions will be there? Just think about it. Let's say if you call for f0 of 5, right? If you call for f0 of 5, what will happen? F0 of 5 will first go to this if check. Is 5 equals to 1? No. So we executed one instruction. Can I say that? This if check is what? This if check is not a loop, right? It's independent to the value of n. It is independent to the value of n. So we can say it's going to take constant unit of time, right? And then it goes to the next line. It goes to the next line. It says return n into and a function call. See, the product of two values is constant. Product is a constant operation, and calling a function is also a constant operation, right? Just calling a function is also a constant operation. There is no loop acquired at all, right? So can I say when you call for f0 of 5, you do this as a constant operation and two more constant operation, that is constant plus constant is still constant. So I can say when you call for f0 of 5, overall you executed constant number of instructions. But here is a catch. By just executing f0 of 5, your whole program is not done. Why? Because when you make this function call, there are two things that are happening. Here. One is we are calling the function. This is the first step that is happening. And calling the function is a constant operation. When you call the function or when you invoke the function, that is a constant time operation. But when you call this function, and this function goes in the call stack, because we know that whenever there is a function call, even if it's a recursive function call, you add it in the recursive call stack. So initially called for f of 5. Now you're going to call for f of 4. Now whatever time this f of 4 is going to take is going to be extra apart from the function call. Can I say that? By just writing f of 0 n minus 1, this is just we are calling or invoking the function. Once we invoked the function, this function came in the call stack and we are here waiting, right? Now how much time this function call is going to take to execute is going to be the extra time. So we have to add that. That is how much time f of 4 is going to take. That is going to be the total time. Yes or no? Okay. Now let's see how much time f of 4 is going to take. If you go for f of 4, you will again compare. Is 4 equals to 1? No. So again a constant time operation. Then you say return n into. So there is a product which is a constant time operation. F of n minus 1. So when you say f of n minus 1, that means you are calling for f of 3. So we are calling the function first. So again total constant time operation you are doing. See, this if check is constant, product is constant, and calling the function is constant. Once you called the function, it called for f of 3. Now how much time f of 3 is going to take to completely execute itself is going to be the extra time. So the total time executed or total instructions required to calculate n factorial or 5 factorial is this plus whatever time f of 3 is going to take, right? F of 3 is also going to take constant operation of time, and internally it is going to call for f of 2 and so on, right? And so on, f of 2 will call for f of 1 and so on and so forth. So what I'm trying to denote here, I'm trying to say that in these kind of recurrences, the total number of instructions can be calculated very easily by saying that number of instructions in one function call multiplied by total number of function calls. Now this is not a general formula. Because there will be cases when this formula might not work. For example, as I told you that there are some special type of recursive relations called as divide and conquer. We'll talk about that. We'll talk about divide and conquer relations, but a lot of recursive formulas we will be able to detect once we will be completing the learning of divide and conquer relations. Then we will be able to very easily detect which recursive relation is a divide and conquer relation and which is not, right? So all those relations which are not in divide and conquer relation, can be almost 99% can be very easily generalized with this formula. Because just think about it. However many number of times you are going to call f of 0, right? Most of the time, until or unless the code that is written in the function is dependent or putting a loop based on this input, till that time, every function call is going to have the same number of instructions. Just think about it, right? So this is going to be the number of instructions. Just think about it. Every time the number of instructions are same. The number of instruction would have been different if, let's say, I would have introduced a for loop that starts from n and goes, that starts from 0 and goes till n. If I would have introduced a for loop like this, then because in every function call the value of n is changing, then this formula will not work, right? Then this formula will not work. But if the situation is something where the recursive relation is not changing the total number of instruction in every function call, then we can use this formula. That is number of instructions in one function call multiplied by total number of function calls. Because here you can see in f of 5 also there is same number of function calls, f of 4 also same number of function calls, f of 3 also same number of function calls. That means that number of instructions of every function call is same. So total number of instructions will be number of instruction in one function call multiplied by total number of function calls. Now just think about it. If this is the function, in every function call you are doing constant operations, and how many total function calls will be there? From 5, this is the first function call, this is the second, third, so on and so forth. Can I say you will make n function calls? From 5 to 1, you will make n function calls, right? In every function call, if you go to this function, in every function call you are making constant operation, there are total n function calls. So can I say total instructions are nc? And what is the complexity for this? The time complexity is going to be order of n. The time complexity is going to be order of n, as simple as that, right? So this is something that we have to do. And as I say, we have to keep a check. If there is a divide and conquer relation, or there is a situation when the functions of recursion are executing different number of instructions in every function call, then we have to manually calculate it. And it was similar in loops also, right? When the constraints of the loops are same, like n, and internal loop is also n, then we were able to very easily decipher n square. But when the overall parameters of the loop change, then we have to manually calculate it, right? Similar thing will happen here. If we can just straightforward see that, okay, in every function call you can see there is a base case, and then there are few products. Calling a function is a constant operation, then it's like overall constant operation. Now internally that function is going to be called multiple times, and due to that we are going to add up a time complexity, and that's why we can use this formula. So we're going to solve a few more questions to get a better hang of it, but this is the overall agenda that we are going to do for basic problems of recursion. Later we will try to understand what is special with divide and conquer. So now we have a new problem in front of us. You can see this is also a recursive code, and if you just carefully analyze, it's a Fibonacci code, right? Okay. Now in Fibonacci, you can see that with respect to n, the total number of operations in every function call is same, right? You can see if you go for f of 5, f of 5 calls for f of 4 and f of 3. F of 4 calls for f of 3, f of 2. F of 3 calls for f of 2, f of 1, and so on, right? So there are multiple function calls that are happening. In one function call, you can see you are having a if check, which is a constant operation. You're having one function call which is constant, you have another function call which is constant, and you are doing addition of the answers of these function call which is constant. So in one function call overall, you are doing constant number of operations. In one function call, we have constant operations. And how many total function calls we can have? Just think about it, right? Just think about it. If let's say you have to calculate f of n calls for f of n minus 1, f of n minus 2. F of n minus 1 calls for f of n minus 2, f of n minus 3. F of n minus 2 will call for f of n minus 3, f of n minus 4, and so on, right? And so on. You can see that from n you go to n minus 1 and n minus 2. If you just see the longest path, for example here, if you see the longest path, then f of 3 calls for f of 2, f of 2 calls for f of 1. If you see the longest path, then in the longest path we are making what? N calls. But it's just not n calls here. Technically, we are expanding like a tree. We are expanding like a tree. Right? We are expanding like a tree. This is f of 1, f of 0. This is f of 0, f of 1, f of 0. Right? We are expanding like a tree. Right? You can see that when you are very close to the lower values, then some of the values are empty. You can see, if you just see this much part, then this tree is completely like full. But here you can see some of the children are not present. Some children are not present, right? So when you reach the very small values, then you can see some of the values are gone. But if you see with respect to very high value of n, let's say n becomes as big as 10 raised to the power 2 or 10 raised to the power 3, then a very big part of the tree is going to be something like this: f of n minus 1, n minus 3, n minus 3, n minus 4. Then here we'll be having f of n minus 3, f of n minus 4, and so on. And if you just carefully see, then every level has some function calls. If you see this level, there are 2 raised per 0 function calls. If you see this level, there are 2 raised per 1 function calls. There are 2 raised per 2 function calls, and so on. So we are having function calls with respect to power of 2. So what is the total number of function calls? Total number of function calls is going to be what? Approximately. I'm saying approximately. I know that at the very last level, there will be some calls which are going to be missing. But approximately, if we assume that everything is present, right? If we assume everything is present, then we'll be having something like 2 raised per 0 plus 2 raised per 1 plus 2 raised per 2 plus 2 raised per 3, so on and so forth. Right? This is what? Coming as a geometric progression. Can I say that? And thus, if you see the sum of this geometric progression is going to be what? First term is 1 into ratio is 2 raised to the power. Total number of terms. Now just think about it. This is 2 raised per 0, 2 raised per 1, 2 raised per 2, 2 raised per 3, 2 raised per 4. So n was 5. So you're going to 2 raised per 4. So final term is going to be 2 raised per n minus 1. That is approximately, this level is going to have 2 raised to the power 0 function calls. This level has 2 raised per 1 function calls, and so on. Final level will be having 2 raised per n minus 1 function calls. So from 0 to n minus 1, total level becomes n minus 1 upon 2 minus 1, which becomes what? 2 raised to the power n minus 1. Sum of this GP is what? 2 raised to the power n minus 1, which is approximately 2 raised to the power n. So we can say overall, in approximate terms, there are 2 raised to the power n function calls. There are 2 raised to the power n function calls. So in one function call, you are doing constant operations. Total number of function calls are 2 raised per n. So time complexity becomes what? 2 raised to the power n into c, which is order of 2 raised to the power n. Can I say that? So the time complexity of this function is going to be order of 2 raised per n. And you might get a feeling that, okay, sir, but at the last level, you are not having 2 raised to the power 4 function calls. Instead, you are just having 2 function calls. That's what asymptotic analysis is all about. We approximate things. Because if n will become extremely high, 10 raised per 4, 10 raised per 3, 10 raised per 5, then even if you have pruned some calls at the very last, it will not matter. Because let's say you prune all the calls from the last level, and you go from 2 raised per 0 to 2 raised per n minus 2, let's say. Still the overall sum is going to be 2 raised per n minus 1, and 2 raised per n minus 1 is approximately 2 raised per n. So in approximate terms, things are not going to change, and hence the complexity of this Fibonacci recursive code is order of 2 raised to the power n. And if you just carefully analyze, what is the complexity of iterative Fibonacci? I'm just writing a pseudocode here. In pseudocode, if you remember, you start with 2, you go to n, you do plus plus, and you do c is equals to a plus b, right? Then you say a is equals to b, b is equals to c. Remember? Right? And at last, in the value of c, you have the nth Fibonacci. So you can see from 2 to n you are going. So from 2 to n there are what? Total n minus 2 function calls, which is approximately n. In every loop, you are doing one addition, two assignments, one comparison, one increment. So 5 instructions. 5 into n is approximately n only. So the complexity of this iterative Fibonacci is order of n, whereas the complexity of recursive Fibonacci is order of 2 raised to the power n. And if you remember, the growth rate of 2 raised to the power n is much higher than order of n. That means this piece of code is slower if you compare it with the iterative code. This iterative code, if you see, that piece of code is slower. Although there are some techniques in which using which you can optimize this code. There are some techniques using which you can optimize this code, but those techniques are currently out of the scope for this particular lecture of time complexity. So there are techniques like dynamic programming and all using which you can optimize the overall time analysis, right? But my point being, if you just go with the plain recursive Fibonacci code, then the complexity is order of 2 raised to the power n. And if you go with this plain iterative Fibonacci code, this is order of n. Hence, this iterative code is better. But again, there are few techniques using which you can optimize both. One small piece of note. This approach of order of n is also not the most optimized approach. There exists an approach using which in order of log n, you can calculate nth Fibonacci. That approach is called as matrix exponentiation. You can read about it. That approach is called as matrix exponentiation. So using some matrix multiplication and matrix analysis, we can calculate the nth Fibonacci in order of log n time. So just a trivia I want to share with you. So now we have a new function in front of us. Now this time, if you just carefully see, inside the function, which is technically a recursive function, because we are calling the function again, we also have got a for loop. So it's now no more like constant number of operations, first of all. Second of all, this for loop is dependent on the value of n. So now we cannot just directly use that formula, right? Now we cannot just directly use that formula. So we have to carefully analyze the question and then only figure out what can be done. Now, generally, in order to analyze the questions like these, I try to take some simple examples. Just think about it. What if I call for f2 of 5? If I call for f2 of 5, this if check is a constant operation plus. This loop is going to go from 1 to 5. Can I say there will be 5 iterations? And then there is a function call. So again, a constant operation. And this loop is also going to execute constant number of times. There are some constant operations here. So for f of 5, you technically did something around 5 plus 2c operations. And then you called for f2 of 4. In f2 of 4, you are going to do constant number of operations plus you are going to run a loop for 1 to 4, which is 4 iterations. And then again, make a function call f2 of n minus 1. That means you call for f2 of 3. In f2 of 3 again, we can write something like this. There, the loop is going to go for 3 iterations and so on. Finally, you will be having f of 1. The loop will just go for 1 iteration and that's it. So technically, if you see, you are doing 5 plus 2c plus 4 plus 2c plus 3 plus 2c and so on. Something like this. So if you see it with respect to n, if we consider 5 as n, that means you are doing n iterations plus 2c plus n minus 1 plus 2c plus n minus 2 plus 2c and so on up till 1 plus 2c, right? This 2c is what? Constant operations. So constant operations though we will avoid. We are left with what? N plus n minus 1 plus n minus 2, so on and so forth, plus 2 plus 1. This is what? Sum of the first n natural numbers. What is the sum of first n natural numbers? N into n plus 1 by 2, which is what? N square by 2 plus n by 2. In big O notation, this term is going to get avoided because this is a lower degree term. And 1 by 2 will also be avoided because it's a constant. So in big O notation, this will be order of n square. So the time complexity for this function is order of n square. So here we manually analyze that, okay, in one function call, you are executing an iteration. Then you're calling for n minus 1. So in the next function call, you're going to execute n minus 1 iterations for the loop. Then you will call for n minus 1, that is n minus 2. So in this function call, you will execute n minus 2 iterations for the loop, and so on. So we will just sum up all the number of total iteration, which will give us this as the total number of iteration approximately. We will just resolve it, avoid the lower degree term, avoid the constant, and order of n square is going to be our final time complexity. So this is going to be the answer for this question. So I hope the overall logic on how we are checking recursive time complexity is clear to everyone. Now this is a new recursive code in front of us, and we have to calculate the time complexity for this code. Here in this code, we have to assume that this ARR is actually an array, and the length of the array can be considered as k. Okay. Now just think about it. If you just carefully see this function, you are doing recursion with the variable n. The value of the variable n changes every time, right? From n to n minus 1, then to n minus 2, then to n minus 3, and so on. The array length remains as it is. The array length is constant every time. That is k, right? So in every function call of f3, you execute a loop of order of k. This loop is of order of k. In every function call, you execute this loop. This is a constant operation. Calling a function is a constant operation. So can I say every function has same number of operations, that is order of k, right? And what is the total function calls? What is total function calls? Total function calls is from n you go to n minus 1, then you go to n minus 2, so on and so forth. You go to 0. So on an average, approximately, there are n function calls, right? There are n function calls. So total function calls are n. So can I say total operations will be order of n into k, and this will be our time complexity as well. As simple as that. So now here you can see in this question, the number of operations that was executed in every function call was same. So we were able to just directly apply the formula, right? So we have to just keep our mind open. We have to just see the situation, what is the expected situation, what is being done. And based on that, we have to calculate our answer. So I hope the overall logic of the problem is clear to everyone. So we have now a new problem in front of us, function f of 4. This function looks a lot similar to the Fibonacci function, but the only difference is here we call for n minus 1 two times. Here we call for n minus 1 two times instead of calling for f of n minus 1 and f of n minus 2. So if you see, from n you call to n minus 1 and n minus 1 only. Then from n minus 1 you call for n minus 2, n minus 2. Same here, n minus 2, n minus 2. Then from n minus 2 you call for n minus 3, n minus 3, n minus 3, n minus 3. Right, and so on. So you can see at each level we are having number of function as a power of 2, so on and so forth. At last we are going to have 2 raised power n minus 1, and in one function call you are having constant number of operations. So the overall time complexity is going to be 2 raised power n, total number of function calls multiplied by time in one function call, right? But I will change the function very slightly. If let's say if I have a function f5 of n, and then I say n less than or equal to 1, then let's say return 1, otherwise return 2 into f5 of n minus 1. Now technically what I have done here is, in the previous function call it was f4 n minus 1 plus f4 n minus 1, which is technically what? 2 into f4 n minus 1, right? Like we could have written 2 into f4 n minus 1, but we didn't. We manually made 2 function calls. But here, instead of making 2 function calls, what I'm doing, I'm making function call once and multiplying it with 2. So let's see what's happening. Now, if you just carefully analyze this, from f of 5 of let's say 10, you make a call to f of 5 of 9. You are now not making 2 function calls. You're only making 1 function call. Then from 9, you're going to call for 8, then for 7, so on and so forth. 3, 2, and 1, and then 0. The moment you get 0, you're going to return 1. Then whatever is the answer here, you're going to multiply 2 with it and then return it to this. Then whatever is the answer here, you are going to multiply 2 with it and then return here. So you can see we are only making n function calls, and in every function call we are just doing a constant operation and a multiplication. So the time complexity for this case is going to be order of n. So in recursive code, the way you call the function can determine a lot of things. The answer of both of the codes are going to be same. The final answer from both of the codes are going to be absolutely same. It is just that here we are only making one function call and using the result to multiply it with 2. But instead here we were manually making two function calls, which was like manually going and calculating all of these operations again and again and then adding both of them. So the way you actually implement your recursive functions can determine a lot of things. So I hope the overall answer of the problem is clear to everyone.